Hi guys. Today we will be solving practice for a particulate nature of matter topic for IB. It fits both SL and HL and it's structure 1.1. So the worksheets would be from Save My Exams. They were so generous. They allowed me to use their worksheets in my IB videos. And they don't not only have IB, so Save My Exams, it's a website. They have a lot of exam practice and they have good notes for for all the topics in A level, IB, GCSE, and some other exams as well. So they also have these exam style questions for the new IB specification, so I highly recommend to check them out. And I will be solving worksheets from their website today and hopefully also in other live streams as well. And the worksheets that I will be solving are medium difficulty because they also have not only topical worksheets, but they also separate them by difficulty. Yeah, so there is easy, medium, and hard ones. So just start with medium ones. And I will link all the worksheets that I'm solving below, but I won't be solving like all the questions because there are a lot obviously, but I'll just choose some that are, I feel like, the more typical ones. So this is from Save My Exams. We'll do a couple of multiple choice questions and some open response as well. Okay, so let's start. Let me see if everything's working. Yeah, I think it's working. Right, so structure 1.1, and here I denoted the level. Yeah, so I think this topic, it's only for SL, but then for other topics you'd see which question I'm solving. SL or HL. Okay, so first question, which equation does not represent sublimation or deposition? So sublimation, it's what? It's when it's a change of state, right? It's when solid goes to gas. So B is sublimation, and we need the one that does not show sublimation. So not B and not C. C is also sublimation. Deposition, it's the opposite. It's when gas goes into a solid. So not D. D is deposition. And the answer is A because A is just, it's a reaction. It's not a phase change, it's just acid-base reaction. So A. Next question. Which of the following is a heterogeneous mixture? Heterogeneous mixture, it's the mixture that has different phases. Yeah, so the mixture where you can see it with the naked eye that you have two substances or more substances there. And let's see, so aqueous solution of copper chloride. If you see the solution of copper chloride, you just see like a pale blue or blue depending on the concentration. Liquid, you won't be able to tell, so there would be just one phase. So this is homogeneous, not A. An alloy of iron, carbon, and chromium. Well, it's an alloy, right? Alloy, it's when everything, like it would look just like a metal. Yeah, you won't be able to tell whether it's just iron, whether they've added anything else. So that's why there would be no different phases, so not B, it would also be homogeneous. A mixture of sulfur and potassium chloride, yes, that's heterogeneous because sulfur, it's a yellow solid, potassium chloride is the white crystals, and when you mix them up, you would definitely see that there are two different substances which are not combined together. Yes, they haven't formed any bonds. That's why it's heterogeneous. And D, a mixture of ammonia, hydrogen sulfide, and methane gases. Well, they're all gases. So if you just have a jar with the gas, you won't be able to tell whether it's one gas or more. So it's homogeneous as well. Question 3. Which statement is correct about recrystallization when purifying a solid? So recrystallization, this is the new thing, I think, in IB, a syllabus where they want you to know different methods to separate mixtures. Recrystallization is one of them. So let's quickly go over it. So what happens during a recrystallization? So recrystallization is used to purify an organic product. So you make some synthesis and organic synthesis, you have a product and you want to purify it. And the first thing that you would do is you would dissolve the impure compound, so the impure substance that you formed, in a minimum volume of hot solvent. Yeah, so what is the solvent? The solvent has to be selected in such a way that it would dissolve well. So appropriate solvent is one which dissolves both compound and impurities when hot. Yeah, so it must dissolve your compound when it's hot. And when you cool it down, so in cold solvent, the compound of like your target product must not dissolve. Yeah, so it does not dissolve well in cold. And what, let's see, why do we need that? Yeah, so first, when we dissolve the impure compound in hot solvent, what happens is that you dissolve your compound and all the soluble impurities. Yeah, so all the impurities that dissolve in that solvent. And then second step would be to filter solution through filter paper quickly. Usually you would also use a heated filter funnel for that to avoid recrystallization on the filter funnel, right? So you want your compound that you're trying to purify to pass through, and the filtration would just remove the impurities that were not able to dissolve. Yeah, so you're removing insoluble impurities. Okay, so this step removes insoluble impurities. And then once you've cooled, then the third step would be to cool down the solution, so the one that passed through the filtrate. So you cool it down, and what happens? Remember we said that the solvent must not dissolve your solid well in cold, right? So when you cool it down, the impurities would stay in the solution because the amount of impurities is much, much lower than the amount of your product hopefully. And then your product would start recrystallizing and impurities would stay in the solution, right? So that's why we needed to use a minimum volume of hot solvent, not just a lot, yeah, because we want to recrystallize our product afterward. It's much easier to do when you don't have much of the solvent. And another thing is that if it doesn't dissolve well in the cold solvent, so again, the crystals are much easier to form and you don't lose much of the product. Okay, then we would use suction filtration with a Buchner funnel to separate, to remove the crystals, wash the crystals with a tiny amount of distilled water to remove soluble impurities, and then just dry. Yeah, okay, so just to recap. So these steps are crucial, and I think those need memorization because everything else, it's like kind of logical and very intuitive, but the first three you just need to know. So you would dissolve an impure compound in small volume of hot solvent. Solvent dissolves your substance well when it's hot and does not dissolve well when it's cold. Then you hot filter the solution to remove insoluble impurities. Then you cool down the filtrate using the ice, for example, on the ice, and your crystals start to reform and soluble impurities will remain in the solution. And finally, you just separate the crystals using suction filtration with a Buchner flask and wash the crystals with distilled water and dry. Okay, now let's go back to the question. So which statement is correct? First, the solid must be insoluble in the hot solvent. Wrong, right? Because it must be soluble in hot and insoluble in cold, so not A. The impurities will remain in the solvent when cooled. The impurities will remain in the solvent when cooled. Yes, that's true. So the soluble impurities will remain and our crystals would form. So B looks right, but let's check the rest. The yield of the product is the same after recrystallization. Well, definitely not. We will lose some crystals. And the solvent is in excess during recrystallization. Also wrong, right? It must be like a small amount. Small amount of solvent. to allow for easier formation of crystals. Okay. Right, next worksheet. Yeah, next worksheet, it's for paper 2. So let me check it. Yeah, everything is seen. Okay. First question. A sample of pure solid sulfur dioxide was slowly heated from -100 Celsius, which is below its melting point, to 0 Celsius, which is above its boiling point. Its temperature is measured every minute, and the results are represented on the graph. All right, so what do we see here? So this is a typical heating curve. Yeah, so similar one you would have for water, but with different temperatures. So the first, the lines that go up, those are the lines where we're heating either solid or gas or liquid, yeah? And the horizontal lines are the phase changes. It's when you have, for example, gas changes to liquid or liquid changing to solid. And so this first line, so we start at -100 Celsius and then go up. So this, they say that a sample of pure solid is heated from -100 Celsius, which is below its melting point. So it means that it's a solid here. So here, From A to B, we're heating a solid, right? Then B to C, horizontal line, it means that it's a phase change. What would be the phase change after solid? Well, obviously it would melt, right? So it's from solid to liquid. Then at point C, we have liquid formed, so it's melted. So from C to D, we are heating up the liquid, right? Because you see temperature changes, temperature goes up. At point D, we start forming gas. So this is changing from liquid to gas. Yeah, again, the phase change. So this is liquid to gas. And after E, everything is gas and gas is being heated. So the y-axis shows the temperature, T is time, so it means that you just keep on heating this substance, right? What's important? So what's important is important to notice that when you have a phase change, you see you don't have a change in temperature, so the temperature stays. Yeah, it doesn't change. And I think there would be a question like that, or maybe not. So basically, the heat that you're supplying when, for example, in A to B or C to D or E, like and above, the energy that you're supplying, it increases the kinetic energy of the particle, so your temperature increases. But then when there is a phase change, then the energy that you're supplying, it is used to break intermolecular forces, yeah, between the particles, or like whatever forces of attraction there are between the particles. Okay. Question. Complete the equation for the equilibrium present in the region BC. BC is what? We said that BC is solid to liquid. Well, it means that SO2 solid goes into SO2 liquid. Yeah, this is at equilibrium. So at at B to C region, you have both solid and liquid at equilibrium. What is the physical state of SO2 in the region after E? After E, it's a gas. Just in some questions, actually, just one word of caution. Yes, so be careful when sometimes they would not start here. Yeah, so sometimes they might start the heating curve here and just say that it starts at liquid. So they don't have to give the entire curve, but you know that there should be two phase changes. And next question is, what would be the difference in the region BC if an impure sample of SO2 had been used? Okay, so what is the difference between the melting point of pure and impure substance? So obviously BC is the melting point, right? So melting point of pure SO2, it's here. Yes, so it's like 60, minus 60 or 70 Celsius. And then if the substance is impure, what changes is that melting point would be lower and it would not be a uniform. So like the impure substance would melt over a range of temperatures, right? And that's actually one way to check whether your substance is pure or not. So, for example, during the organic synthesis, if you want to show that your substance is pure, you have to measure its melting point. And when you do, if it has a sharp melting point and if it matches to the melting point of that substance from the data booklet, even better. But in any case, even if you don't have the melting point for that substance, you just measure it. If it's sharp, then you can say that it's pure. If it melts over different temperatures, so like you're heating, it starts melting and then it melts and melts and melts for ages, that means that your substance is impure. Yeah, so basically BC would not be horizontal, but it would be it would be aligned with the slope, and also it would be lower. Yeah, so we can say that melting point would be lower. That's one mark, right? So for one mark, that should be enough, but I would also add that it would melt over a range of temperature. So, and it would melt over a range of temperatures. And how would we see it? Well, we would see it as BC not being straight, yet not being horizontal. Would not be horizontal, yeah, would not be horizontal. Or would have a slope. That's too much for 1 mark, right? Obviously, but in questions like this where you don't really understand what they want from you, yeah. So what would be the difference in the region BC? So do they want to just you to know to show how the region would change, yeah, or would they maybe just accept that melting point is lower? So in questions like this, when I don't know exactly, when I don't recognize the question, I have never seen this question before, I haven't seen the mark scheme for this question, I just write a little bit more answers. Yes, so maybe not 1, but 2 points even for 1 mark, just in case. Because when you're writing 2 points and one of them is not in the mark scheme, you don't lose a mark. They just ignore everything that's not in the mark scheme. And if you have a statement that is in the mark scheme, you just they just accept that. The only, like, you only have to be careful with, like, without, so that you don't give any contradictory statements. Okay, so if you say, for example, that melting point would be lower for the impure sample, and then somewhere you say that melting point would be higher, well, obviously one of those statements would be correct, but you lose a mark anyways, because, well, because this is a contradiction. But as long as you don't contradict, you can give several answers. Of course, it doesn't have to be like it doesn't have to look like you're betting on answers, yeah, but if they ask for 1 and you give 2, it's fine, yeah. All right. Next, using the graph in part A, complete the table by comparing the separation and movement of the molecules in regions A to B. So A to B was what? A to B was, we said, solid, right? So this was solid, and C to D was liquid heating. Yes, so liquid. All right, so distance between particles. Well, obviously in both solids and liquids, particles are close to each other. In liquid, but in liquids they have slightly more movement, freedom movement, right? So I would say close to each other in both. But in liquids, maybe they're slightly further apart, yeah, so when they have a little bit more freedom to move. And movement of the particles, well, solids, yes, the particles vibrate around fixed position. In liquids, particles move around past each other, and past each other, past, past each other in a random motion, yeah. So vibrate around a fixed position. Here they can move past each other slowly and randomly. Yeah. And ability to move apart. So in solids they can't move apart. Well, this in liquids they have a bit more freedom, but not as much as in gases. Yeah, so I would say they. I would maybe repeat what I already said. Yes, they move past each other, but not freely entirely. Yeah, so this is actually a weird thing to ask, to be honest. But let's say cannot move far apart. Yeah, far apart, but they can move apart a little bit. So obviously they have more freedom than solids, and the proof for that is that liquids can occupy the volume of the container. Yes, so they have more freedom to move, um, because they can, like, fill the whole container, while solids would not do that. Yes, this is. I hope they don't ask you this in the exam, or the mark scheme would be generous. So that's a weird question. All right, next, 1C. Explain why the temperature remains constant between B and C. So between B and C, it was phase change. It was from solid to liquid, right? That's melting. Yeah, so as we said, the temperature stays the constant in the phase change because the supplied energy would be used to break the bonds of attraction between particles, right? And once those bonds have been broken, then the temperature would start increasing, yeah? Then the energy would turn into kinetic energy of the particles. Right, so because explain why the temperature is constant, because all the heat energy supplied energy is used to break. I don't want to say intermolecular forces. Here I could say that because it's about SO2, so it's a just simple covalent compound. But just in case maybe, yes, so what if they don't give you a simple covalent compound? I would just say that to break forces of attraction between particles. To break forces of attraction between particles, to move them like further apart. Okay, next question, question 3. Skip some questions because they're either not entirely topical or they're very easy or just don't look like exam style, so I'd skip those. 3A, during SL as well, yeah. During the manufacture of a commercial drink, a batch containing water, sugar, dyes, and flavoring concentrates became contaminated with an unknown solid during the mixing process. Right, so the drink, obviously it's a homogeneous mixture, was contaminated with solid. State the type of mixture that best describes this batch. Well, after the solid has been introduced, that becomes heterogeneous mixture. 1 mark, good enough. Draw a labeled set of apparatus required to isolate the solid particles in the mixture. Well, maybe I won't draw it, but I'll just show you. Yeah, so this is just, well, this. So this, let me show you again. So draw a label set of diagram required to isolate the solid particles in the mixture. So they want to separate solid from the solution, right? And the filtration, it's the technique that is used to separate insoluble solid from liquid. Oh, and that's what you have to draw. So this would be filter funnel, filter paper, solid and liquid, and they also asked a label diagram. So maybe I would also denote a beaker. So I'd say this is a beaker. This is a conical flask. Yeah, I think that's good enough of a diagram. And this is how it looks in real life. Yeah, so this is your beaker. This is just a glass rod, filter funnel, another beaker or conical flask, doesn't matter. Yeah, so that's how it looks in the lab. So this I consider we've done. Yeah, I showed you the picture. It's okay. Just 2 marks actually. Next, 3B. State the method that could be used to isolate the dissolved solids such as dyes and flavorings from the mixture. So after you've removed solid, yeah, that is insoluble in the liquid, what is left? Well, what's left? It's just the solution of something. Yeah, the solution of some soluble salts such as dyes and flavorings. And to separate solid from a solution, we would use crystallization. Yeah, so we would just evaporate water and the crystals would stay. So that is crystallization. Yeah, so it's used to separate, to produce solid crystals from a solution. So that would be called crystallization. When we evaporate water, evaporate the solvent, yeah. Right, and then state the method that could be used to separate the dyes and flavorings once they have been isolated. So, okay, so you evaporated the solvent and now you have a mixture of solids. And this is not an easy task. So, to separate the mixture of solids, hopefully those solids would have different solubilities. If they do, then you can use the recrystallization method. And I think that's what they mean here. Yeah, so you just recrystallize, and because different dyes and different flavorings would have, well, the flavorings meaning it's like probably some esters, yes, some substances. So different substances would have different solubility. We would assume, and different solvents, yeah. So you can combine, and you can test different solvents and different temperatures to make sure that one substance dissolves, another doesn't. But the method, they don't ask for specifics, right? And hopefully you don't have to do it. Like, luckily you don't have to do it. So, but you can just, in general, in theory, you could use the recrystallization method, right? Because some substances would be more soluble in the solvent than others. What solvent that must be, it's a whole different question. Yeah, so they don't ask about it. Recrystallization. And let's see. Okay, I hope we have time to finish this question. If not, well, hopefully, yes. Okay, let's do it quickly because I have a lesson starting. So once the flavorings have been separated, chromatography is used to identify them. So chromatography is used to separate substances. Usually they should be like colored, yeah, or at least some substances which you can later detect, even if they're not colored. So probably you need to use some locating agent, or they would be visible under the UV light, like amino acids or proteins, yeah. But let's see, they say flavorings. Well, I would maybe instead of flavorings ask about dyes, but it doesn't matter, yeah. So they are separating some substances using chromatography, yeah, paper chromatography. The sample was labeled as X. Okay, so they placed the X sample here, and A, B, and C are reference flavorings, and then they place A, B, and C dots, yes, so substances at these points. So A, B, and C are known flavorings, right? And then they run this whole thing through the solution. Like they run the solution goes up the chromatography paper and takes away the dyes and the sample with it. Right, and we see that our sample has separated into 3 spots. What does it mean? Since it showed 3 spots, it means that there were at least 3 dyes, yeah, that were not dyes, but like 3 compounds, yeah, at least 3 different substances that separated, that were able to separate. With chromatography, we can never tell for sure, right? Maybe one spot would contain a mixture, like you can tell unless you do some other test. But here, what do we know? So you see, the substance C traveled this far, and substance X also has this spot, right? It means that substance X had substance C in it, in the mixture. Also, we know that B traveled this far, and substance X has the spot at the same level as B. Yeah, so it traveled as far as B, which means that the mixture X contains the substance B. And it contained one more, yeah, one more substance, which we don't know what it was, yeah, because we didn't have any control for it. So we know that it didn't contain substance A, because there is no spot here, but we know that it contained something else. Yeah, so basically we know that this spot is substance B, this spot is substance C, this spot is unknown. The reason why they would be the reason why they move in different to different heights, it's because different substances would stick to the paper differently due to intermolecular forces, or like whatever forces of attraction they have to the paper. And second is because they would have different solubility in the solvent, right? So okay, let's see. So identify which flavorings are present in sample X. Well, we said it's B and C, right? But not A. Yeah, not A, because there is no spot at the level of A. And identify, giving a reason, the least soluble flavorings for 1 mark. So least soluble would be the one that traveled the least, right? So to the lowest height. So it's substance C, which means that it wasn't dissolved and it was stuck to the paper. So substance C. Yay. Okay. Right. So I will link, as I said, oops. Yes, as I said, I would link the worksheets below this video, so you can solve them, or you can just check and see some other questions there. Yeah, because I skipped question 2. I think maybe I skipped some other questions, so you can see the entire worksheet there. And next time, I think I will continue solving worksheets. You can request the topics if you'd like. Yeah. Okay, so see you next time.